Hey there. Let's perform searches in a binary search tree. Okay, if you watched my previous videos, you know how to define a binary search tree by now. You know some terminology. You know how to construct a tree. And so now let's just take a tree that's already been constructed and let's search through it. First thing I want to say is this is a binary search tree. This is not a self-balancing tree. So in the future, this tree could get lopsided and messed up depending on what kind of data we add. We can always expect that binary search trees have a search time or an insert time or removal time of log base 2 of n on average, assuming that the data is random, or in the worst possible case scenario, linear time. So these could get slower. Right now, you can see this tree is perfectly balanced. So if we say that our tree is currently perfectly balanced and it's always going to be perfectly balanced, which is a fantasy, but let's just say that it is, then we could just say it's a log tree. It's going to take log time to search through. So how do we perform searches? Again, if you saw my previous videos, you should know that it's really easy to find out where a node belongs. Like, for example, if I was going to add the number 14, I would first, look at the root node and I'd say, okay, the root node is occupied. And so where would 14 belong? Well, it would belong on the left of 37 because it's less than 37. It would belong on the left of 16 because it's less than 16. It would belong on the right of 9 because it's greater than 9. It would belong on the right of 11 because it's greater than 11. And so the 14 node that we just wanted to add, is that what I just said, 14? Would end up going there. So when you're searching through a binary search tree, you really just have to go find where the node would belong, as if you're performing insert. Or you could think of it the other way around, like insert is really thinking of a search first. But basically, we're just going to start by saying, pick a number and we'll see if it exists. So let's pick the number 67, or actually let's pick the number 73 just to see if it exists in the tree. So 73, I'm going to do like, 73 with like a question mark. We check the root node. 73 belongs on the right side. We look at the 59, it belongs on the right side, and we found our 73. So 73 exists in the tree, and it only took us 3 examinations. Only 3 examinations. Let's look for a number that doesn't actually exist in the tree. So maybe, oh, my thing is freezing. What's going on? Okay. So maybe let's look for the number 44. So if we look at 37 here, 44 belongs on the right of 37. We look at the 59. It belongs on the left. We look at the 48, it belongs on the left. We look at the 43, it belongs on the right. The 44 would have been there, but it's not because that right child pointer off the 43 is null. So we only had to really examine 1, 2, 3, 4 nodes in order to determine that our number 44 didn't exist in the tree. Notice how we're not doing a lot of examinations compared to the total size of the tree. So let me just write this up here. How many nodes do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We got 15 nodes up here. Someone say n is equal to 15. And what's the height of the tree? Remember, the height of the tree is the number of nodes you must touch as you make your way down towards the deepest node. Or if you've already found the deepest node, you take its depth and you just add 1, assuming that depths start at 0. So I'll just say that the depth of the root node is 0, and the 59 and the 16 are 1. And then that third row is 2, and that last row is 3. And then I just add 1 to the deepest node that I can find, which is just going to have a depth of 3. All of these on the bottom row have a depth of 3. So the height of this tree is actually 4, because we would have to touch 4 nodes along the way to the deepest node. So like 37, 59, 48, 43, that's 4 touches. Or the depth of the deepest node plus 1. Okay. All trees, all binary search trees, whether they're actually AVL trees or regular binary search trees, or whether they're balanced or imbalanced, they're always going to have a time complexity to search through of O of H, meaning in the worst case scenario, you'll have to touch H number of nodes, where H is the height, in order to find a node by search query, or to add a new node, or even to delete a new node. So how does that compare to this tree in reality? Let me just open up a little calculator real fast. I just want to show you. So if we do log base 2, because we have a binary search tree, not a trinary search tree or something, log base 2 of the number of nodes, 15, it tells us that it should take us no more than 4 examinations to find the node that we're looking for if the tree was perfectly balanced. And if you notice, that's exactly what the height is telling us here. If the tree was more imbalanced, the height would get really bad compared to the number of nodes, and it would no longer be considered a log tree. It would just be, you know, somewhere in between linear time and log time. Let's see, what else can I show you real fast? Let's do, well, we did that computation. Let's do a search through the tree, through a tree that's actually really, really bad. Let's pretend that we have a bunch of nodes here, and you know, I've got an old story that I love to tell about this. When my grandma was alive, she was kind of bitter towards the end. You know, I loved her, but she used to call the cops on her neighbors for gossip. And at some point in time, she got into a feud with her neighbor, who was also a bitter old lady. You know, towards the end, it kind of happens sometimes. It sucks, but it happened. And I guess the neighbor didn't like my grandma's tree that she had in her backyard. So they fought over it, they argued over it, and then one day my grandma said she was looking out the backyard window to yell at ducks who were jumping into her pool, because she just hated when the ducks went into her pool. She was waiting for them to show up. She wasn't even looking at ducks, she was just waiting. And she saw the other little old lady reach her arm over the fence and spray my grandma's tree with some sort of poison. Then my grandma's tree died, and I guess, you know, my grandma never got over it. I always thought it was like a funny story. It was a little sad, but she poisoned my grandma's tree. So we can kind of do the same thing with the binary search tree. We can give bad data. Let me show you what happens here if I use this data set on a regular binary search tree. So we're going to add this node right here. It's going to be the 14. And then when we add the 19 node, I'm just going to duplicate it. The 19 is supposed to be on the right side of 14 because it's greater than 14. So I'm just going to, like, you know, draw a 19 right here and a little connecting line. Okay. Then when we add the 24, I'm going to duplicate this node over here. Where does the 24 go? Belongs on the right side of the 14, and it also belongs on the right side of the 19 because it's greater than 19. So again, we have a node that shows up on the right side. Let me remember to actually fix the 19 so it looks like 24. Then when we add the 29, it's going to end up being the same thing, right? The 29 is going to end up showing on the right. It's going to just be on the right side of the 24. So if we have bad data, we can end up with a tree that kind of looks like a straight line. And if you are watching this video from the future, after I've posted my all of my data structures videos that I have, you might notice that this looks like another data structure. If you're watching this right away, I haven't posted those videos just yet, but just tilt your head to the right a little bit and tell me if that looks like something that you recognize. It looks like a linked list, just like a straight line, or even, I guess you could kind of say maybe an array, just like a straight line of data. There's no, you know, there's no splitting of the data. So we have the 29 and then the 35, and then maybe I'll just do one more node only, and I'll get rid of that 54 because that's too many nodes. So what happens is, if you have, you know, bad data in your binary search tree, then your binary search tree doesn't actually search or add, insert or remove or anything like that in log time anymore. Instead, it operates in linear time, just like a linked list would, meaning we would have to scan through every single node in the entire tree to be sure that some value did not exist. Well, not exactly, but in the worst case scenario, we'd have to scan through the whole entire tree. So, for example, let's just look at the number of nodes real fast. We'll say the number of nodes here is 1, 2, 3, 4. Oh, I put two 24s in there. Oh, dearie. Let me get that. It's 14, 19, 24, 29, and then I guess I forgot to make that a 35. Oh, okay, and then there's a 49. I guess I did add every single node. Okay, so we added the whole entire data set. 1, 2, 3, 4, 5, 6, 7. So there's like 7 items in the tree. So I'm going to say n is equal to 7. The height also is 7, though. So the height is 7. Notice how if we say that it's always true that a binary search tree has a time complexity in the worst case of O of H, meaning you'd have to go down in the worst case the number of levels that is equal to the whole entire height of the entire tree. That's also the number of nodes in the tree, which means if I wanted to add, let's say the number, I don't know, if you wanted to add the number 60, 60 would end up going down here, and in order to find where 60 would go, we'd have to look at the 14, that's 1, 19, 24, we'd have to look at all these nodes. That is 7 nodes. We'd have to examine 7 nodes just to figure out where the 60 would go. Or if we were searching for 60, then we'd have to go down that far to find out that 60 didn't exist. So this is nowhere near a log tree. This is a linear tree, a linear time tree. And just to drive the point further, if we did log base 2 of the number of nodes, in this case 7, notice how it's telling us that we should, if it was a log tree, if it was perfectly balanced or a self-balancing tree, we should have to touch no more than 3 nodes in order to find what we're looking for, to search through the tree or to insert a new node or even to delete a node. But that's not the case here because the tree is really, really slow compared to a perfectly balanced tree. So we'd call this a linear tree. It sucks. You want to try to avoid that. You don't want your data to be poisoned. On average, your trees won't really look like this if you just have totally random data. But if you think there's a chance that your data might be skewed in some way, it's probably a good idea to upgrade to a self-balancing tree, which we're going to talk about later. Okay, what else can I tell you real fast? So we talked about searching. Oh, why are these trees considered log time? I mean, they're really, really fast, but why? Let's just duplicate this slide here, and I'll move it down one level. I just want to kind of show you why this ends up being a log time tree. Okay, so why? Why is this a log time tree? Suppose for the sake of argument, we're searching for the number 52. So if we're searching for the number 52, we're going to look at the 37 node, the root node, and decide where would the 52 belong. Let me actually write that down so I don't forget. 52, question mark. Where would the 52 belong? It would belong on the right side of the 37 because it's greater than 37, right? Which means it's actually impossible that the 52 would be in any of these other nodes on the left side. There's no need to check them. We're not going to scan the whole tree. We're just going to go left or right and ignore the whole other side of the tree. So if you think about it, what we just did is with one examination, we eliminated half of the remaining data set, or I guess of the initial data set if we're looking at the root node. So then the next thing that we do is we just kind of say, okay, it belongs on the right side. So we look at the 59 node and we do the same thing. We say, where would 52 be? Would it be on the left side or the right side of the 59 node? It would be on the left side, which means we're going to eliminate from consideration the entire right subtree of the 59 node. So again, we're eliminating half of the remaining data set. Then we kind of go down here and we look at the 48. We do the same thing. 52 belongs on the right side, so we eliminate half of the remaining data set, And then eventually we do find the 52, and then that's it. So if we're eliminating half of the data set with every single just one examination at a time, that's why it ends up being log base 2. In other words, if you were getting twice as close to your destination at every step you took, if you're like in a car or like running, maybe you're on the moon or something, then it would be a log time, progress towards your goal, or eliminating half of the data set at every single step. Sometimes people see for loops on exams and stuff when we talk about this, like for I equals 0, I is less than the data set, size like n, and then to advance I, it would be like I times equals 2, so I is jumping twice as far each time. That's the sort of thing that makes it log. So I'm just going to write down log here real fast to drive the point home a little bit more. O of log base 2 of n. Yeah, so I guess that's all I wanted to tell you in this video. Hopefully you feel like an expert in searching now. If you want to see more searching videos, leave a comment or something like that. But yeah, thank you for watching, and I hope you learned a little bit of stuff and had a little bit of fun. I'll see you in the next video. I'm going to go find a blueberry muffin. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. if you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.